Well, what an exciting title. More details later on in a minute, because there are two topics I would like to cover: process understanding and cost efficiency. Cost efficiency or cost savings. That's only possible once we have understood the grinding process. That's the starting situation. I would like to begin by asking the audience the pictures which you can see in the background and the scenario, what do they have in common? Just think about it. This looks like a force diagram, circles of different shapes. So these are conditions most probably leading to bad surface grade or surface quality. And down there you find the situations. On the left hand side you see a grinding disc which cracked. The second one is just one with material agglomeration on it. In the middle we have a grinding process where there was manual roughening before. On the very right hand side we have the picture of an imbalance, and on the extreme right tool breakage. And on the opposite are some erratic conditions. So these are the conditions occurring in grinding. There are influencing factors and determinants like the process parameter as such, the clamping situation, the state of the grinding disc, the type of the grinding disc, of course, with different effects, and further process determinants like lubricoolant, the employee, the operator, the time of the shift, the machine influence, and the material condition. So these are all criteria to be controlled by the grinder. And that's why you would like to have an understanding of the process. So you want to have a stable process. We want to have automation also in individual part manufacturing. And we want to try to avoid downstream cost and time intensive processes, or at least we want to integrate them in the process. So against this background, I would like to cover the second question. Now, the effects, how can they be covered, the effects just described before, on the basis of the grinding pressure and grinding forces, all measured directly at the grinding disc with our spike system. I would like to present you with this system under the title Digital Machining and Grinding, how by using the grinding pressure you can get a better understanding of the process. That's again very good for process administration or process flow and for saving costs. My name is Lennart Riehle. We're in Kaufbeuren, just an hour's drive away, and a warm welcome on behalf of my company pro-micron. So how does it work, this spike system? We've got the measuring technology right behind the grinding disc on the tool holder. That is to say, we have a standard tool holder and we change it into a sensoric one. So we measure the forces Z direction, the torsional moment, the torque, and also the radial forces on the disc. But it also works with milling, other machining types. Here we are on grinding, so the radial forces are measured as well. And this is how I get this circle, because the system is turning, and on the right hand side the grinding pressure acting on the grinding disc is indicated and displaced. Let me give you a bit more of detail. You have the sensors on the holder. That's a typical mandrel, grinding mandrel, 20 diameter. And you have the grinding wheel. At the moment you have no no rotation from the X direction. For example, if you press onto the tool, your force signal in the X axis is shown. For example, in the Y direction, if you press this, then it's the other way. So if you turn it through machining, you get this picture. So that's an animation. You see the X component, then comes the Y component, and our spike polar. So these are the forces acting on the grinding wheel, the bending moments as well. And if in this area, if you have a material agglomeration there, the picture looks like this. So actually, by way of the acting forces, we can cover this condition, and on the grinding disc we can also localize it. So that's the basic principle behind our measuring concept. The sensors are on the holder, then we have radio transmission, of course, to the receiver connected to the laptop. You can pick up the measuring data, change something in the process, recapture the data, and you can have an influence and you can compare. And this is how you gain in addition to the result, you already have some understanding of the forces, the conditions acting during the process. So these are the raw data, as it were, the rough data. Now we want to illustrate them and make them more graspable, as it were, so that the machine can do something with the data as well and take a decision or react. Perhaps we can derive a reaction. So we have our measuring and monitoring concepts of the KPIs. We have the force values over time. We have our spike polar in the radial view. And the dots, you know, the number of the measuring data can be reduced, and nevertheless we still see the effect of a focus shift. And with these reduced data, smart algorithms can be used, key process indicators, for example, so that a certain value between 0 and 100 can be made available, and with this value a machine reaction could happen. So in the past few years, by the way, the spike system was commenced in 2012, and later on grinding came in addition, and this all on the holder. So we have some use cases. This is a system which can be used along the value creation chain. Of course, you want to have some understanding of the grinding process. Later on, perhaps a little bit more, you know, partners, customers, users, in other words. Here you've got 5 application examples, which I would like to give you some details thereof. And for example, by using the parameter optimization, we get a better understanding of the process. Measuring data I've brought along, you know, so that you can see the difference between machine roughening and manual roughening. 3 breakage situations were sensed. So to show you how it works, the system. And the system actually was covered by a funding project, so that we can test out the limits and the possibilities. And we also have a hand in the development, you know, in the development of even more sensitive sensors, as it were. So in the series, in connection with one manufacturer, you know, we picked up the status quo, and that's the blue graph. We know the value, the force level. The steps are slightly different, and with the cutting dotted parameters marked in blue, you have the spike polar. And it's not quite centric. In top left we have these little waves flattening on the right hand side, and what happens if this cutting speed is stepped up? But what's the effect on the grinding disc? And you can see the force is rising though, but the grinding disc is much more centric and truer, has a truer running. And so the operator, the process expert, just by using this, you know, gets a very nice status picture, like a doctor measuring the fever in a patient, for example. The expert can do that as well using this measuring system, which is a lot faster. Now, here in the running series, we compare two grinding discs with each other, same processing, different manufacturers. You see one uses a lot more force than the other one. Simple comparison, digital application technician, you know. It not only helps the customer, they can use it by themselves, but also the disc manufacturer. You can use the same system for optimizing his own products or testing it. For example, the end user Kennametal, for years he has been using this system not only for testing the milling and the drilling units, but they have their own grinding center and their development or test machines. And such a holder being used so that the process conditions can be tested out during grinding for integrating some important data in the series production. And they have this kit, you know, that goes the same kit that go to the series machine and sends the forces and measure them as well. So some weeks ago, together with the machine manufacturer, grinding machine manufacturer, we ran that test. We just wanted to find out about the sensitivity. Is there a force difference between machine and manual roughening? And here you see the conditions. Machine roughening, then next 3 people doing it manually. It looks quite interesting. The application engineer did quite a good job. Then the manager wasn't that good. The next one. And here these were just simple tests which we could do in our test center to see the different influences of the grinding pressure. So here we have various balance running tests and qualities. Blue and green are compared with each other, G1 and G3. As far as the force level in torsion is concerned, or in the bending moment, that's the same. That's identical. But when you have a look at the spike polar, you see there is a shift of focus because, you know, it's co-turning this action of the force, and you can see this and identify this in the spike polar. Now, using this concept of smart algorithms, an offset parameter could be established starting from 0.0 and as 0.5 shifting focus, red marking, so the machine can visualize this, but you could also have a reaction by linking or connecting a machine. This is an example from a completely different grinding area, not just tool grinding, is this powderous material in ceramics manufacturing. And the customer just wanted to know when is the disc, the grinding disc, agglomerated with that much material that it has to be replaced or whatever, and or when should the ground object be removed, for example, because of a certain grinding condition. So this is what we took as an example, and I asked him, you know, when would he do the roughening? Track 5, that looks quite well, but track 7, he had a look at it and the measuring data as well, and that would have been the moment, you know, for direct reaction on the machine. Yeah. Reacting. Well, I called it wear and tear here. Several processings were carried out. Fresh roughening in blue, bronze is worn out and worn down after 5 tools, and green is after 2 parts. And I just want to indicate here, you know, the spindle current to be read with a percentage indication. This is an enormous help in assessing machine operation. But when it comes to monitoring and details and quality assessment, then of course we have another possibility here, using the direct force measurement and get even more information out of it for, you know, covering the ideal condition, and react accordingly. It not only works in the torsional segment, but also via the bending moment. Here we have 5 objects. So 5 components. We have a force increase of 37%. We will be doing a long-term test before long. I'm not a grinding expert though, but I think you are a grinding expert, and the grinding disc should cut itself free. And when is that moment? And does it happen in the right moment, or using these parameters or influence parameters? These are the very things you can cover and work out and test out, and not just through long-term data or experimental values. And data. Again, the same principle applies. Once you know the action of what force and which effect, with which effect, then a KPI value could be established, okay, and connected to the machine for reaction. Always force-based. Potential benefit, which I would like to cover and discuss at our stand, when it comes to process monitoring and understanding, needs-based roughening and dressing, how using these data, the automation degree of my manufacturing process, how can it be improved? How can the number of rejects be reduced, or identify whether a batch has some bad elements as well? You get a good documentation and process transparency, even using digital twins, more or less, this term. And force value goes in line, and for customers, this is a big target in the future. One aerospace manufacturer is very interested in the grinding data of the tool, because here maybe there were some influences on his surface finish he has to do and document. Now, process monitoring. That's the Achen Institute, Tool Institute. They have a spike system like this, not only a system for the grinding disc, but also a spike system for the forces on the blank that were measured as well, the bulk. In a milling process, a spike was used, and various process conditions were recorded and evaluated, deviated, analyzed with spindle current data. And this is an output of a research project where machine manufacturers, end users, grinding manufacturers, tool manufacturers were all involved. They also use such a system for better understanding of the process. The system has to be perfected, and we try to get as much information as possible. Internal and external cylindrical grinding are some conditions, for requiring higher sensitivity, more rigidity of the holder, the tool, and higher revolutions, 18,000 revolutions. That's limited. Internal cylindrical grindings, of course, the number of revolutions is a lot higher. And these are the data which we sort of cover in connection with funding projects and some institutes, and we are involved so that your products and your requirements can be optimized on the basis of these forces, or at least that you have a better understanding of the process. How can this measuring technology be used for what applications? As an assistant, how the spindle current, like in percentage terms, a spike could be run as well for analyzing the data. You remember the first pictures, this cracking disc. Once you see this, then it's easier to understand and explain these effects. And then he knows, okay, I've got to do something. That's pure assistance. The main tool used in the value creation chain is diagnosis. That's the main tool, expert tool, measuring rate of 2.5 kilohertz. You cover and capture the data, you record them, change something, re-record the data. You can compare and analyze for better process understanding. Holders, the tools can be the same. Instead of the blue receiving unit connected to the laptop, you can the black box with a machine control, could be linked with a machine control, and and connected to other interfaces, automated for recording, measuring data, and reanalyzing or analyzing them later on, and react accordingly. Now, in brief terms, what do you want to reach with the spike? This condition of the 360-degree condition of the disk can be assessed. The process errors can be identified, for example, imbalance, out of round running, or some vibrations not desired. More efficiency is to be achieved because of the forces, and we can then draw a conclusion in connection with the quality. Optimization is a big theme. And of course, in some respects, the steps as far as cost saving is concerned with optimum conditions and optimum parameters, all this can be implemented in a faster way, documented, confirmed in a faster way, and captured all in all. And that's a big savings potential. It's important to say this. It's a plug-and-play system. We don't plug-and-play system. We don't have any cables. We have different holder types. The sensor has to be located and seated on the holder. It's plug-and-play. We see a manufacturer, for example. We want to get a better understanding. Okay, attach the disk. And we connect it to the laptop, and measuring starts automatically, plug and play within 1 minute. And another point, not only in tool manufacturing in terms of the institute, but also the grinding disc manufacturer, and above all the end user. Of course, the tool grinder, Metal, for example, they use this system on the test machine or on the series machine for better process understanding. Thank you very much for your attention. Now we can ask, or I can take your questions. I can also take your suggestions. We're right around the corner, Hall 7 here, not too far away. And we have several spikes, and check out for yourselves, how it works. Thank you very much.